All right. Hello, everyone. Welcome back to Physical Geology 1403. Today is lecture 9. We are learning about glaciers. Woo! I'm excited. Glaciers are fun. I'll remind you all why we talk about glaciers here in a minute. But before that, let's do our usual round of announcements/questions. So, your next exam is going to be after the next 3 lectures, including today. Okay, so you still have a couple of weeks. Do the same preparation for that you did for your most recent one. Make sure your notes are up to speed. Make sure that they are things that you can rely on. Quiz each other if you find that is helpful. If you have not completed all 4 of the identification labs, please do that. I will be getting you lab 5 sometime soon. It may be next week. It might be the week after. We'll see. We'll play around with it, see how ready I think you are. Lab 5 is not on the lab exam. It is all about reading maps. It has nothing to do with identification. So after you're done with lab 4, to your satisfaction, you're done with identification until the lab exam anyway. Okay? So let's see. What else? Our class movie night is going to be October 4th in that room over there. Wood Math and Science 203. And yes, my online students are more than welcome to attend that. It will be at 6:30 on October 4th. If you're watching this after that, I apologize. It's too late, right? You obviously can't watch that. You could watch the movie entirely on your own, complete the extra credit assignment. I cannot stream this movie for copyright reasons, obviously, so you will need to be here in person. The movie that won, can I get a drum roll, please? 2012. We are watching the End of the World Disaster movie, 2012. Huh? Is it an actual movie? Oh, an action movie. Yes. It is an action overload movie. Yes. You've seen it, Jocelyn? Yeah. I actually watched it with my friends a couple weeks ago. We were trying to decide what to watch. I did an experiment. I set up my projector screen so that we could just hang out in my friend's pool and watch a movie. We were all just like hanging out on pool floats watching a movie in the evening. It was awesome. And we're like, what should we watch? We're like, we could watch Hidden Figures about, the women in the astronaut program. We could watch The Help, right? Or we could watch 2012. And everyone was like, 2012! So we watched that while we were hanging out in the pool. It was really fun. But yeah, that's the movie that won. So we're going to have a good time. There will be a small extra credit assignment associated with that. This is mostly for fun. The extra credit is just there as an additional yay, right? But come and have fun. Bring food, snacks, college appropriate drinks. You know what I mean by that. Feel free to bring family or friends. I have tons of chairs over there. I think there's like 30 chairs over there, and we can move the tables however we want. So we'll just make a night out of it. Okay? 6 o'clock, October 4th. Good deal? Awesome. Okay. It's always fun when more people come. I've had it where there's like me and one other student, and that's kind of awkward and not as fun. But then when 20 people come, it's a madhouse. We have a good time. It's at 6 o'clock. Yes. When will it end? Probably calculate somewhere around 8:30 to 9. It depends on how much discussion we have afterward. I kind of leave it up to y'all if you want to do the extra credit assignment together afterwards. So you can bring your laptops, open them up after, and then we can discuss the 4 or 5 questions that I ask about the movie right then and there. Or if everyone just needs to leave home, you can do the questions on your own and we get to leave a little earlier. So calculate somewhere between 8:30 or 9 for when we're done. It's a little over 2 hours, the movie is. Okay. What can you bring for food? Anything you want. Whatever. The louder and crunchier, the better, right? That's etiquette for watching a movie in a group, isn't it? Everyone just brings chips, and all you hear is, right? Okay. Yeah, whatever you want. I don't eat out very often, like normally once every couple of months. So I might pick up Taco Bell or something like that, just to be a little, huh? You've never had Taco Bell? Yes, no, it is not. It does not feel good. It tastes good. it doesn't feel good. That's why I don't eat it that often. But I'm just like, I've been thinking, I'm like, you know what? You have Taco Bell at home. Okay, let's move on. Questions. What questions do you have from either our last lecture or anything we've discussed in the class so far? Or world events? Any world events that have caught your eye or your attention? There's been a little bit of volcanic activity on the Aleutian Islands, but that's not weird. There have been a few earthquakes out in the Pacific, but that's not weird. We had our earthquake here on Sunday. We already talked about that. We had a 5.1 on Sunday. I don't know if you felt that or not. I did. You did? Okay. Actually, I think it was on Saturday. Yeah, I'm pretty sure it was on Saturday. Okay. No questions? Are you ready for this lecture? All right, then let's dig in. Before we talk about glaciers, we need to talk about water. Let's talk about some of the amazing things that water does, some of its amazing properties. Water is very unique. And when I say that, let me give you a little bit of perspective here. Universally speaking, water is not unique. Okay? Water is actually the most common 3-particle molecule in the universe, as far as we can tell. Okay? You look out into space and you look at all the wavelengths of light that are bouncing off things in space, like clouds of gas. So much of that is water. Earth having water is not terribly unique. Having liquid water, now that depends upon specifically being in a zone around our sun that we call the habitable zone. That's kind of the distance, the right distance from the sun where the temperatures are not so extreme that either all your water remains in a gaseous state, like what happens on Venus, right? Venus is too close. It's right there on the edge of the habitable zone. So it has a very thick carbon dioxide and water vapor atmosphere, but no oceans as far as we can tell. And then on the other side of that extreme is Mars, which has only frozen water because it's too far from the sun and doesn't have enough of an atmosphere to maintain liquid water. We are right smack dab in the middle of the habitable zone. Good for us. So we have liquid water. Okay, and we'll talk about what role that played in allowing life to exist, to begin and exist here. We'll talk about that more when you take my 1404 class next semester. Okay, but for now, let's focus on water itself. So water is everywhere in the universe, but liquid water specifically. Let's talk a little about that. Water has a property we call cohesion. Can any of you explain that word to me? When you have like two droplets of water, okay, so that's an example using water. Let's focus on the concept of cohesion first. What is cohesion? What does the word mean? Huh? The unity of something? Okay. In simple terms, let's call it something sticks to something else, right? You can use cohesion in a lot of different contexts. These sticky notes are having cohesion with each other. They're stuck together, okay? You can think of it like that. In the case of water, you're absolutely right. Water likes to stick to other water. That's why when you're driving down the road, right, and it starts to rain and you notice drops of water are kind of just staying on your hood or maybe on your windshield if you stopped at a light, they're just drops of water. It's not spreading out really, at least not until it starts raining a lot and there's more water available. But when it's just individual drops, they just kind of hang out on your hood or your windshield. They stick together. If I had a plane of glass and I put a droplet of water on that glass, what would it do? It would make a little bubble of water, wouldn't it? That's cohesion. Water likes to hang out with other water. Now, if I took, let's say, canola oil or vegetable oil, and I put a little drop on that glass, what's it going to do? It's going to spread out. Oil is significantly less cohesive than water is. Matter of fact, a lot of things are. Some things are more cohesive. Some things are less cohesive. But water, one of the properties that is important to today's discussion of water is that it is cohesive. Okay? That's why we have, lakes. and rivers. Water likes to hang out with other water. It doesn't spread out wherever it can go, at least not as much as many other things. Okay. Now, it absorbs heat very efficiently. It takes a bit of energy to heat water up, but then it also takes a while for that water to cool off, right? You fill up your bath with nice hot water, it'll be a couple hours before it cools off, right? This is a concept that actually played a lot in the role of our early civilization. How do I mean? Well, picture, if you will, a coastal community that relies upon fishing as a major industry, or maybe even just to support themselves. Maybe they don't even export it. They just go fishing to support their own community, okay? They need to go where the fish are. The fish are usually some distance out from shore. Now, how do you get there? You can either row or you can have a sail, right? Sailboats have had a long history. But the sailing relies upon having wind available to push you where you want to go. Now, at some point in the past, someone figured out that in the morning, there is a strong breeze that goes from the land out to sea. And in the evening, there is a strong breeze coming from the sea back to land. And it tends to correspond with sunrise and sunset. Now, I didn't exactly understand why that was at the time, but let me explain it to you. Because of the fact that water absorbs heat so efficiently, that's why. Because land will heat up quick and lose heat quick. The ocean will heat up slow, but lose energy slow. Okay, it holds on to it longer. So if my land is warming up fast, all of a sudden it is emanating heat upward, right? It's radiating that heat back up into the atmosphere. We have warm air above the continent and cooler air over the water, which is heating up cooler. It's basic meteorology, right? Warm air moves into cold air. High pressure zone, low pressure zone. Breeze from land out to sea. Then in the evening, when the land is cooling off faster and the ocean that has had more time to heat up and is holding that heat longer, that makes warm air above the ocean. And so in the evening, you get the opposite effect. Warm air from the ocean moving in over the sea or over the land. And so you get the breeze that takes people out in the morning and brings them back in the evening. That's actually where the concept of our workday came from. You wake up with the sun, you go out and fish. You come back with the setting of the sun when the breeze brings you home. 9 to 5 is what we call it now. Although, depending on where you are in the world, it could be anywhere from 6 to 8, right? It really just depends on the season. Okay? Okay, so it absorbs and holds heat very efficiently. And then here's another fun thing about water. When it is in its solid form, which we call ice, it is less dense than its liquid form. This is not typical. Normally, when you take a liquid of some kind, let's just say rock, okay, magma, liquid rock, and you crystallize it, it condenses. It becomes denser. Not so with ice, not so with water. What happens when water freezes? It expands by approximately 9%. It will actually expand. What does that do to the density? It lowers the density. Why? What is changing? Remember, density is a measurement of mass per unit volume. What is changing? Am I changing the mass that I have? No, what am I changing in my equation? What's the other thing? What's the other component? Volume, exactly. I am increasing the volume while maintaining the mass. Therefore, my density decreases. Therefore, solid water will float on liquid water. Yeah, very unique. Not so with most other substances. Okay. Now, why are we talking about this? What does this have to do with geology? Someone remind me. Glaciers are made out of ice, which is a mineral. Why is ice a mineral? What are the 5 properties of being a mineral?
That's the chemical composition.
Chemical composition. Crystalline form. We got 3 more. What do you think? Shout them out. You should know by now. If you're wrong, I won't make fun of you. Unless you're Angel. I can say that. He's not here. Okay. What else? What are the other 3? I appreciate those of you that are looking through your notes. Let's figure this out.
Inorganic, solid.
Inorganic and solid. And the last one? Naturally occurring. Those are the 5 characteristics of a mineral. Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. That's a mineral. That's ice. Ice, ergo, boom bada boom, is a mineral. And therefore, today we are learning about glaciers because it falls under the category of geology. So, glaciers, ice, mineral. It has all those characteristics. However, when you exert certain stressors on ice, it behaves in weird ways. Again, this comes down to some of those characteristics that we discussed earlier. Okay. For example, even though ice is a mineral, a mass of ice, which we typically would refer to as a glacier, it moves. The movement of a glacier we describe as plastic. It is behaving plastically. What is plastic? I know this is a weird question to ask, a weird one to think about and answer. What is plastic, though? Shoot your shot. What do you think? It is a product, right? This mineral cleavage form is made out of plastic. I printed this skull out of plastic. Most of the computer components in the frame of this laptop are plastic. This case is plastic. This remote is plastic. This camera has a lot of plastic in it. Your phone has a lot of plastic in it. Your shoes have a lot of plastic in it. There's plastic all around us. Plastic is a word that we often use to describe a series of polymers that we can shape into whatever we want. There are literally hundreds of types and recipes for making plastic. So I want you to not think of plastic in terms of a substance. Why do we call all these things, all these different recipes for these different man-made materials, why do we call them all plastic? Not because they are all the same thing, but because they all have the same behavior. So now I want you to think of plastic not as a subject. I want you to think of plastic as an adjective. Plastic as an adjective means something that is moldable, changeable, formable. Okay? So when I say that a glacier moves plastically, it has plastic behavior, that means it is molding and reshaping. But by what? We will talk about that in a little bit. Okay? So, glacier, very thick masses of ice. These things take a very long time to form. Where do you suppose the ice is coming from, by the way? Camera, stay with me here. Huh? It's happening on mountains, as we will discuss here in a minute, but where is the ice coming from? What has to come before the ice does? Water. Where does the water come? Usually in the form of snow. We'll talk about that process more in more detail here in a minute. But imagine how long it takes for snow to compact into thousands of feet of ice. Okay? Most glaciers are anywhere from a couple hundred to maybe 1,000 feet of ice these days. Back during the last ice age, there was a glacier about a mile thick sitting on top of what is modern day Ohio and Wisconsin and the Great Lakes area. Okay? Oh, we'll talk about that. Okay? Now, even though glaciers are ice, and therefore they fall into the category of rock, they are also still a phase of water. And so this is one of those fun, unique circumstances that we talked about, where 2 cycles can interact with each other. In this case, the hydrologic cycle and the rock cycle. Because ice is a mineral, it is part of the rock cycle. Because ice is also water, it's part of the hydrologic cycle. And so the two cycles intermesh here. As our glaciers are moving, they are also being extremely powerful forces of weathering and erosion. Look at all the material. What do you think this dark stuff is on top of my glacier there? It's not grass. Yeah, those are rocks and dust and all sorts of other mineral material. All that is being carried downhill by this glacier. Stuff that we'll elaborate on in a little bit, but I just wanted to show this to you so you can see that, yes, they are not only grinding and crushing all the rock in their path, but they're carrying all that material downhill. So they are weathering and eroding simultaneously. Yeah, there are a lot of glaciers on our world right now. As a matter of fact, fun fact, technically speaking, an ice age is a period of time when there is ice at both poles of the planet. Do we currently have ice at both poles of our planet? Yes, we do. Technically speaking, we are in fact still in an ice age. Everyone screams and cries about global warming, and it is a real thing. I don't want to underplay that. And we will discuss that, some today, some later on. But we are technically still in an ice age according to the definition of needing ice at both poles. We are losing ice at both poles. It is true. It is melting. As a matter of fact, if you took all the ice into Antarctica and melted it, that's about 65% of all the fresh water on our planet is tied up in the glaciers on Antarctica. So if you melt all of that, our sea levels rise about 60 to 70 meters. Okay, now that is a very long-term possibility if that is going to happen. Right now, we're looking at maybe 1 to 1.5 meters of sea level rise by 2100, okay, at our current rate of warming and melting. That's not insignificant. It is going to displace communities. It is going to be problematic, especially for places like New Orleans or some places in California, New York, places that are already so close to sea level that a 3-foot rise is actually pretty meaningful. You and me here in Odessa doesn't mean a whole lot to us. There will be some things that matter more to us as global warming continues, but we will talk about that later, okay? If you took all of that and you melted it, take a look at what happens to our United States. Our Gulf of Mexico has expanded. Florida is gone. Matter of fact, the Gulf of Mexico has expanded all the way up to Memphis, Tennessee. Memphis is underwater. Houston, way underwater. San Francisco is underwater. San Francisco Bay is huge now. Seattle is underwater as the Puget Sound has expanded upward. New York, underwater. Pretty much the entire East Coast is underwater, actually. The Great Lakes have increased in size as well, as has Hudson Bay. Most of those larger Canadian cities built around Hudson Bay, those are gone, right?
And of course, we're still in the desert.
And we're still, hanging out here. Yeah. Yes. Yeah. Florida is gone. Sorry, Disney World. So long. Actually, so I did a class for my PhD last semester where I needed to pose a possible, a hypothesis for one thing that could impact communities as sea levels rise. Sea level rise and charting that and tying into glacial melt rates. That's what my PhD dissertation is about, right? And so this was something that I was quite interested in. And so I wanted to come up with something that was unique and fun and interesting that no one had done before. And so I wrote a news article, like a fictional news article, about how sea level rise had caused the Everglades in Florida to flood. The sea levels were rising, the Everglades became flooded, and the alligator populations were therefore moving north into human communities and were threatening communities in northern Florida as the Everglades were flooding further and more and more and more. And so people were abandoning towns as they became invaded by alligator populations fleeing the Everglades. My teacher loved it. She was like, "This is really cool and interesting and probably going to happen." I was like, yeah. Okay. Let's talk about the different types of glaciers that we can see, all right? The most common one that you'll probably see the most often, this is called a valley glacier. You want to guess why we call it a valley glacier? It's a glacier in a valley. Well done. Okay, so they are usually in these nice, wide, U-shaped valleys, but they don't start off as that. They typically start off as more V-shaped body of water sort of valleys, kind of like a stream valley coming off of a volcano or off of a mountain range of some kind. But as time goes on and more ice moves through that low point of that stream valley, the ice chews away and removes so much material that eventually you get that nice rounded U-shaped glacial valley instead. Now what you can see here is that two glaciers have combined, the Valerie Glacier and the Hubbard Glacier, okay? And they have combined and made a larger, much more monstrous glacier right there. We'll talk about that process here in a bit, but it empties out into Disenchantment Bay down here. This is in Alaska, by the way, okay? I did go to Alaska earlier this year, and I took a ton of pictures. I spent a day up on a glacier collecting samples, hiking around. It was so much fun, but I unfortunately didn't have enough time to put any of those photos in this presentation. So instead, I'll probably send an announcement to everyone later today with some of those pictures so you can see your professor hanging out on a glacier. It was really fun. It was a good time. Highly recommend Alaska. Also Iceland. Love the glaciers in Iceland too. Okay.
Did you try the glacier water?
I did try the glacier water.
How was it?
It was so cold, it hurt my teeth, but it was so pure. There are two places that I've tasted the water, and it's been the cleanest, purest water of my life. Like, I literally felt like the toxicness of normal civilization and all of the impurities leaving my body as I drank it, right? Think of Lear Park in Iceland. It's that picture that I showed you earlier in the semester where I was scuba diving between the two tectonic plates where it cuts Iceland in half. And there's that park. It's filled with natural glacier sourced spring water, but it has taken 10,000 years to filter from the glacier through the basalt and end up at this park. About 10,000 year process. And it's the most filtered water you'll ever have in your life. And then earlier this year, when I went and I spent that day up on the glacier in Alaska, I found a pool, just a pool of water hanging out on the glacier. Blue, so blue. And you just like, you dip your hand in it, and the moment that your hand goes in the water, it's so cold you can't feel your hand anymore. Like, it's like, oh, I'm numb. Oh, my teeth hurt. That's so good, right? Love it. Best water ever. Okay, a couple of other types of glaciers. Ice sheets. Ice sheets are truly massive bodies of ice that are fed from a central source. There are only two on our planet right now, okay? First one being Antarctica. All of this ice, all these glaciers over here on the outsides of Antarctica, that's all fed from deposited snow here in the middle. And so it kind of spreads out from there, and it feeds all of these glaciers and ice fields out that way from this central area, okay? And then the other one is Greenland, okay? Most of the deposition is over here, and then it kind of spreads out from there. Those are the only two ice sheets we have right now. We've had more. There have been times when we've had absolutely none. There is a period of time when Earth was completely covered in ice, except for a very narrow strip around the equator. Again, we talk more about that in 1404. We call that snowball Earth. That's one of the closest that life on Earth has ever come to dying. There was nothing alive at that point that we know about except for bacteria, but most of the bacteria died, and only the ones that were living around that narrow strip of unfrozen water on the equator, that's what survived, and then life, kind of diversified from there. And then there have been plenty of times when Earth has been so warm that there's been no ice anywhere, as far as we can tell. Okay, we're kind of in an intermediate phase right now where we are coming out of an ice age still. And then we've got ice caps. An ice cap is very similar to an ice sheet, except it tends to occupy a single local area, like a mountain range. And so, yeah, you have multiple glaciers, but they're fed from the same central source. It's just not covering a large area. It's covering a localized uplifted area like a mountain range. And then we have outlet glaciers. An outlet glacier is simply a glacier that has kind of gone rogue from an ice sheet or an ice cap. You can think of it like that. It's kind of off doing its own thing. It's like, you know what, forget the rest of you. I'm just gonna wander my way down here. Okay, that's an outlet glacier. And then a Piedmont glacier looks like this. Okay. Now, before I explain this, I want to see how many of you can try and explain it to me. Tell me what this shape reminds you of.
I'd say a delta.
It reminds you of a delta. How interesting. Describe to me what a delta is again.
Flow from, I guess a flow of water or liquids into a bigger body of water.
Okay, so water flowing into a bigger body of water, yes, but what is happening that makes the delta itself? That's what the water is doing.
Or traveling from one area to another.
What is traveling? The water and sediment that the water is moving and carrying, that suspended load and the bed load. And when that moving water, the river, let's say in your example, hits the larger body of water, what happens to all the carried material? It drops out. The energy that's been moving it in the river all of a sudden has been absorbed by the larger body of water, and everything that's been carried by that energy just falls out. This is true. This is how you make deltas. This is how you make alluvial fans. Does that not look like a delta and an alluvial fan? That's exactly what's happening here. Piedmont glaciers are the same process. But wait, Professor Hart, we're talking about solid water, not liquid water. How does that work? Because water is awesome. Okay? When you have solid water, ice, behaving like glaciers do, it takes on some of the behaviors, the characteristics of liquid water still. How crazy is that? It will still behave the same way that running water will to make an alluvial fan or a delta. Cool. All right. We're going to cook up a glacier real quick. Someone tell me what we need. What are some things we need to make a glacier?
Ice.
Ice. Ice, baby. No?
Before our time.
Yeah.
Like a knife to my heart. Do you all even know that song? Do you know that song? Ice, ice, baby. All right, stop. Collaborate and listen. Ice is back with a brand new invention. Something grabs a hold of me tightly. Flow like a harpoon daily and nightly. Will it ever stop? Yo, I don't know. Turn off the lights, huh? And I'll glow to the extreme. I rock a mic like a vandal. Light up a stage, wax a chump like a candle. No?
That was cool. But I've never heard that version before.
Wow. Okay. Look it up later. Okay, so we need ice, but where are we going to get ice?
From like mountains, like where
On mountains. We need altitude. The most reliable place to get ice is high up in the atmosphere. Why?
the temperature drops in higher places.
That's true. The further up in the atmosphere you get, the lower the temperature is. Why? Why does the temperature get lower the further up in the atmosphere you go? What's happening? The further up you go,
What would be relative to the air pressure?
air pressure is going to decrease for a similar reason, actually the same reason that I'm looking for. What's happening to the air?
Getting thinner.
It's getting thinner. Our atmosphere is thinning out the deeper or the higher up you go, right? So with less dense atmosphere, solar radiation, right, that is constantly striking our planet has less stuff, less molecules, less gases to interact with and stay. So the closer you are to the Earth, the more we have heat because we have thicker atmosphere preventing solar radiation from leaving. But the higher up you go, the thinner the atmosphere gets. Yes, your pressure decreases, so does temperature. Think of it as getting closer to space, atmosphere is getting thinner, and therefore less heat remains, okay? So up high, somewhere above us, there exists a line, an invisible line. Don't look, you can't see it. It's not gonna be out the window, okay? That's the ceiling, Aaron. It's okay.
Are you sure?
Yeah, positive. But you can kind of think of it like a ceiling if you want to imagine that. Call it the snow line. And above this invisible line, snow can remain year round. It is cold enough that snow can remain year round. So if some body of land, say a mountain range, rises up and some portion of it goes above the snow line, what's going to happen above that snow line? Ice is going to form, snow is going to fall, and it's not going to melt. It stays year round because it's above the snow line, and you're going to form ice. And the ice piles up, and you eventually get something thick enough to be a glacier. Okay? I'll show you a picture of Mount Kilimanjaro here in a second. But first, I want to talk about snow. Snow. What is snow? Frozen water. Simple. Easy. Cool. Give me more. Have any of y'all ever seen a picture of a snow crystal? How many of you learned, maybe your mother taught you this, maybe some science teacher taught you this, that there are no snow crystals that are ever the same? Y'all ever learn that? What a lovely, fanciful thought. It's not true. Sorry. Just lies. Shattered your childhood right there. It's on the floor, right? No, there are actually only about 26 possible hexagonal shapes that snow crystals can form, okay? But the reason why that myth came up is because how likely is it that you're going to see repeats of the same pattern if you look at, there are 26 possibilities. If you look at a bunch of snow crystals, how likely is it, unless you have a bunch of them in a microscope and you're doing this before they all melt, how likely is it that you're going to see copies? Not terribly. And so that's where that myth started. People were looking, they were like, wow, that's unique. Wow, that's different. Wow, that's different, right? It's, yeah, now it's water. It's gone, and I can't confirm whether it was the same shape as the one I looked at 5 minutes ago, right? So now we know better. But some time ago, that's where that myth started. Regardless, you get snow and it falls, and it remains, and it gets blown this way, and it gets blown that way, and as it gets moved and shoved up in a pile over here, and then blown this way and shoved up in a pile over there, eventually the crystals kind of start to break down, and you don't have those nice hexagonal shapes anymore. You kind of have this rounded, stubby sort of shape. We call that firn, F-I-R-N, firn. Still like individual crystals, but you can't really call it snow anymore. It's more like ice pellets, tiny little ice pellets, okay? And as the firn piles up, it is that firn that eventually gets compressed down into our glacier ice. What does this process sound like to you? We have crystals that fall, they get moved, and they get moved this way and that way, and eventually they stop and get compressed into a solid mass. What part of the rock cycle? Yep. Sedimentary. Yes, that's how you make a sedimentary rock, right? You get debris like sand, right? A crystal that's been broken down, right? And it gets moved and washed and blown, and eventually it gets deposited. And after it gets deposited, more stuff gets deposited on top until eventually enough pressure is reached that it can crush and cement itself and make that sandstone, right? Is that not what I just described to you and how we make a glacier? There's another parallel right there. Glaciers, rocks, minerals, all of that. Fascinating. Same physics at play, different materials. Okay, so it compacts down from our firn ice into glacier ice. And this can take a long time. Really fast, if it happens really fast, is on the scale of decades, okay? Most of the time, this takes centuries. And if you're in a really long, extended glacial cycle or ice age, then we're talking thousands and thousands of years that these glaciers build up. That's how you get ones like what we had that are a mile thick sitting on top of Ohio, right? Okay. Now this is Mount Kilimanjaro. Anyone want to guess where Mount Kilimanjaro is?
America.
Why would you say Africa? Oh, there's a giraffe. Look at that. Yes, it's in Tanzania. That's in Africa. Okay. Now, what do you see on Mount Kilimanjaro? There's snow. There's ice. Matter of fact, those are all glaciers. You see those? Those are glaciers. But starting right here, there is snow. Now, if I say Africa, you don't usually think about snow in the same sentence, do you? Not typically. And yet, why is there snow on Mount Kilimanjaro? Because of what? Huh? It must be above the snow line. Okay, yes. From here up, we are above the snow line. Snow can remain year-round. Glaciers form. Even though it's in a place that's usually really hot like Africa. Cool on that concept? Awesome. Okay. Let's talk more about that plastic behavior I mentioned before, that plastic flow. For ice to reform itself, for it to bend, for it to mold, for it to be flexible and shift, it needs to be under a substantial amount of pressure. What can provide that pressure, do you suppose? Material piling up. Yeah. Weight provides that pressure. Remind me, what is required for weight to exist? We talked about this when we learned about gravity, right?
Yeah.
Okay, what is required for us to have weight? You need two things. The first one I already gave to you.
The object.
And the object has what? Mass, perfect. And? I already just said that word, this word not too long ago. If I go to the moon, is my mass changed? Gravity, exactly, there it is. If I go to the moon, my mass hasn't changed, but what has? The gravity, and so I will weigh less. I'll be able to jump 8 feet in the air. If I really wanted to, I'll slowly fall back down. Not because my mass has changed, my weight has, because the gravity constant has changed. Gravity on Earth is constant, right? So what do we need to increase? Mass. If we want more weight, while gravity is constant, we have to increase the mass. So how do we increase the mass? We pile more ice up. And as that ice gets piled up more and more and more, the ice on the bottom is under a lot more pressure. And finally, it reaches a point at which it no longer behaves as a strict, rigid solid. It starts to behave plastically. It will deform according to whatever the texture, the landforms underneath of it are. And that's how glaciers start moving downhill. It takes approximately 50 meters of ice before you have enough weight to cause ice to deform plastically. So you won't usually see any movement in glaciers, at least not plastic movement, until you have something that is at least 50 meters thick. Okay? Pretty thick. It's a lot of ice, making a lot of pressure from all that weight. And so the bottom of the ice, the bottom layers of ice are going to deform and allow the mass of the glacier to move downhill, kind of flowing over whatever it is on top of. Now, there is another form of movement called basal slip. This can occur before and during plastic flow. Basal slip is basically when your ice is a little bit colder than the rock it sits on. Perhaps there is some source of heat emanating from that rock. Maybe you're near a volcanic range. You're on the glaciers, perhaps maybe on a volcano itself. And there's a little bit of heat And so that rock is a little bit warmer than the ice. And so there's a thin layer of water that develops as a barrier between the two substances. And every now and then, your glacier will just kind of slip a little bit downhill. Slip a little bit. Slip a little bit. That's called basal slip. Okay? Now, the rate of movement in our glacier is kind of weird. One would think our glacier would just move downhill at about the same rate, assuming that conditions are all the same. If I conduct an experiment and say year 1 of my experiment and year 100 of my experiment, the same conditions exist for that entire time. Temperature remains the same. I would expect that my glacier, all parts of my glacier, would have moved the same distance during those 100 years, right? And yet, in 1874, in the Alps, there were some shepherds that would come down into the fields, or into the cities, come out of their fields, their high mountain fields, come down into the cities, and they would tell people, hey, yeah, you know those big walls of ice up there? Yeah, those move. Because, it's like their grandfather would tell them, yeah, that used to be here. And then their dads would say, well, now it's here. And then they would see with their own eyes, now it's here. But people didn't believe them. And so finally, it got to a point where in 1874, some scientists actually went up there to check if this was true. And they planted stakes in a straight line across this section of glaciers. Straight line all the way across. They came back in 1878, 4 years later, and you know what they found? They found that instead of having moved downhill, first of all, they found that they moved in the first place, which proved the shepherds were right. But instead of having moved downhill, this is their original line, right? Instead of having moved downhill a certain distance in a straight line, they had done that.
It's like the river.
Say that again.
Like the river.
Tell me how it's like a river.
Because the center of it is like the faster moving part.
The center is a faster moving part. How about that? They came back in 1882, and it was even more exaggerated. Yes, the middle of the glacier is moving faster than the sides, just like in a river. Yet another example of how solid ice can behave like liquid water. How interesting. Water's crazy, right? How about that? That's the theme for today. Water is crazy, all right? Any questions about plastic flow? All right. Well, let's continue our conversation about the formation and longevity of glaciers then. You're all familiar with a budget, right? Do you know what a budget is? I know some of you are in high school. If you have not learned what a budget is, believe me, at one point soon you will need to, okay? You and I, we think of budgets in terms of money. What does it mean? More money in than hopefully money out. Although every year that passes, that's harder and harder to make happen, right? It's a struggle for everyone these days. We're not going to talk about inflation, recession effects on any of that, global economies. We're not going to dive into that. For now, just bear in mind a budget should mean more in, less out, overall well-being for you and your family unit. Excellent. Okay, good job. You're making it work. Glaciers also have a budget, but what do you think their budget has to do with? Not money. What do you think a glacial budget would need to balance?
How much water melts or how much ice melts?
How much ice melts versus what?
How much accumulation?
More snow. Snow accumulation versus ice melting at the bottom. Okay, so let's talk about that. Where our snow accumulates, which is above what again? The snow line. Good. Above the snow line is the zone of accumulation. Okay, that's what we call it. Anywhere that has the potential to add more mass to our glacier is in the zone of accumulation. Anything below the zone of accumulation, there is the potential for loss. We call that the zone of wastage. Okay, so zone of accumulation, zone of wastage, and that can include everything from melting to glacier chunks breaking off. We call that calving, by the way. Don't know why. It's like whales have calves, cows have calves. When a piece breaks off a glacier, we call it calving. It's interesting, but I didn't name it. So any loss is called ablation. You may see that in some of the literature, in some of the additional materials that you read. You may see the term ablation. That simply is referring to loss from a glacier. Okay, and that happens in the zone of wastage. When a glacier is losing more at the bottom than it is gaining at the top, the front of our glacier gradually moves uphill. Why? What's happening here? Is the glacier somehow saying, ooh, it's too warm down here, I'm going to pull myself back up? Is that what's happening?
No, more water's going down. That's what they-
There is more melting than there is addition of snow and ice. And therefore, it's still pushing forward. It's always going to keep pushing forward, but it's not pushing forward at the same rate that it is melting. It is melting faster, and therefore the front of our glacier retreats uphill. Not that the glacier is pulling uphill. That's physically impossible, right? It's simply melting faster than it can be restored. So we call that a retreating glacier. Okay. What about when the opposite is true? What happens if we are gaining more snow and therefore adding more ice than the melting rate? What's the front of our glacier going to do? Keep moving further downhill. We call that an advancing glacier. Advancing glaciers are moving downhill because they are receiving more than they lose. Retreating glaciers are retreating uphill. The front is retreating uphill because it is losing more than it gains. Most glaciers in our world right now are in a state of retreat. There are only a few that are advancing, and they're usually pretty far extremes, okay, either in altitude or at a pole. Okay. Any questions? Cool. Okay. Let's talk about weathering and erosion as a result of glaciers. Ice is a solid. Even when it's behaving plastically, it is a solid still, right? In the same way that that Play-Doh is a solid, but you can mold it and shape it, right? Therefore, as a solid, whatever that ice mass, whatever that glacier picks up, it's going to carry with it. It's crushing its way downhill. It's grinding that rock into dust or into smaller pieces. It's going to pick that dust up. It's going to pick up those tiny little pieces, and it's going to carry it on downhill with it. It's along for the ride. So what that means is wherever that ice melts, you're going to end up with all that stuff being left behind. Whatever that ice carried downhill, wherever it melts, that's where that stuff stays. We call that plucking. So if a rock is picked up at point A and then dropped at point B, it's been plucked and deposited there. Huh? Exactly. It's like me picking this up and putting it right there. Same process, right? That's it. Now, when that happens, we tend to call that stuff that's been dropped there glacial erratics. Okay, we have some names for that. When you have a big chunk of rock that has been dropped somewhere by a glacier and has no business being there, look at that big old boulder. What's that doing there? There's no reason why that should be there. And yet, look behind it. There is this big, wide glacial valley. What do you think happened here? It fell off the valley. I mean, who knows where that rock came from? I mean, I can figure it out, right? If I were to do an analysis of it. But what do you think happened? Why did that rock end up here when there is nothing nearby? You think it fell off that valley, rolled downhill, rolled up this hill, and just ended up here? No. What must have happened?
It flowed down with the glacier.
It got picked up by a glacier, plucked, carried all this way, and then when that ice melted, it was dropped there. That is a glacial erratic. I lived in Ohio for about 3 years as a kid. And when I did, there was a state park about an hour from my house Loved this state park. Spent a lot of time there. Me and my friends would go. Next to the parking lot was a massive granite boulder, about the size of a house, a 2-story house, a very modest 2-story house. Big. We'd climb up on that. We'd eat our lunch on the top. It was awesome. We loved this boulder. It was made out of granite. There's no granite in Ohio. It's a bunch of shale and limestone, some sandstone. Mostly it's just Ordovician limestones and shales. There's no granite. So where did this rock come from? Where did this house-sized boulder come from? Well, I'll tell you where there is granite. North in Canada. This boulder was carried down into Ohio by that mile-thick glacier during that last ice age. Plucked up in Canada, taken all those miles, and then dropped right there in Ohio. And there it sits for teenagers to climb up and have lunch on it. Okay?
The glacier, Laurentide ice sheet was in Canada?
Sorry, we say that again?
I can't say it. I might be wrong.
Yeah, Laurentide ice sheet. Yep. One of many ice sheets that existed in that over and over as time goes on. The last ice age, we call it the Wisconsin. There was one, and then the ice age before that, there was another long history of advancing glaciers coming into what we call the United States now, out of Canada, right? Just going back and forth across North America. Okay. Now is when I pull out a bottle. Hooray! Visual representations are always fun. Okay, let's talk about some of the landforms here. Okay, first of all, we've got our nice, lovely U-shaped valley. I'm going to hold it here so that people in the camera can see too. Nice U-shaped valley right there. Did not start as a U-shaped valley. Probably started off as some sort of stream. But what happened that turned this into a glacial valley? Well, perhaps the stream started off coming down from a low mountain area, or maybe not even there wasn't even a mountain there to begin with. But something happened, something tectonically. It's funny how often this all comes back to tectonics, isn't it? Okay? Something happened tectonically, perhaps convergence of plates, perhaps local uplift due to a change in the mantle. Whatever the case may be, that area started getting pushed higher and higher and higher and higher. And what happens then? If some part of my mountain range goes above the snow line, I start to accumulate that ice. All of a sudden, my stream valley that once had flowing water in it to maintain, and it maintained that kind of sharp V shape that we see in the cross section of the streams and the valley stream, the stream valleys. Okay, all of a sudden, ice starts flowing down there, not water, and the ice carves out this big wide U shape, and eventually you end up with your great big valley here. Okay, that's our glacial valley. A cirque, C-I-R-Q-U-E, cirque. Okay, those are the sort of tributary valleys containing smaller glaciers. Okay, that's a cirque. That's a cirque. What happens here is you get multiple glaciers coming out of these cirques, and they combine and make even larger glaciers further down the mountainside. Let y'all catch up in your notes there for a second. And arête, those are these ridges. Arête. And a horn are when the arêtes kind of meet together and form a peak. So like right here, where this arête and that arête meet, that's a horn. This arête, that arête, this arête, that's a horn. That's a horn. That's a horn. Wherever arêtes meet together to form a peak. Usually at the conjunction of two cirques. Now, y'all ever heard the term fjord before? Fjord? You've heard of it? Fjord? You've heard of it? Remember, a glacier forms because there are temperatures low enough for there to be ice. But that snow line up in the atmosphere, that's not constant. Can you think of a situation, a global situation, let's say, there's a little clue, in which that snow line would drop lower? An ice age. In time periods like ice ages where global temperatures drop, guess what? That snow line above which snow can remain year-round gets significantly lower, which means snow can remain year-round in a lot more places. Where is that snow coming from? Snow is made out of water. Where does that water come from? Clouds, right? Where do those clouds come from? Evaporation from the ocean and other bodies of water around the planet. So if water is evaporating from our oceans and other bodies of water, going in the clouds, falling as snow, remaining as ice, it does not make it back into the water cycle. It gets stored as ice around more and more of the planet during an ice age. What happens to our sea levels? They drop. So if I have an ice age and my sea level is dropping as a consequence of all the water getting stuck in the ice, stay with me, camera. Right here. Hello. Right here. Yes. Right here. I'll just stand here for a minute. He doesn't want to move. If all that water is stored as ice, and our glacier can carve even further and further and further down because the sea levels have dropped, more land is exposed, our glaciers are carving their valleys trying to get to sea level, wherever that is. They're going to carve their way down to sea level. And now all of a sudden, let's say, turn on the heat. Ice age is over. Ice is melting. Sea levels are rising. So we have our same valley. We have our same valley minus the ice. What's going to happen to my valley as sea levels rise? My valley has been carved all the way down to sea level. Sea level where it was during the ice age. Sea levels are now rising. What's going to happen to my valley? It's going to get filled with water. That, my friends, is a fjord. A fjord is what we call a drowned glacial valley. Drowned meaning it is now filled with water. All the water has been returned to the ocean from the glaciers that existed during the ice age.
But it won't go back as high as it did, right?
No, it won't fill the entire valley, no. It will fill up the bottom part of it up to wherever sea level is now, right?
So it's not really a cycle then,
right? Fjords are the erosional consequence of the water cycle, I guess you could say. The glaciers doing their thing. No, the fjords themselves are not an integral part of the cycle. They don't exist everywhere. You have tons of fjords in Norway and Iceland and Russia and New Zealand, and Alaska, but you don't have a lot of fjords, in Massachusetts or New York. They're not everywhere. It depends upon what the geology was at the time. Okay, what the geography was actually is far more relevant. Okay, everyone understand fjords? Cool.
Clear as mud. Clear
as mud. I like to hear it. Okay, a roche moutonné. I desperately apologize if anyone is familiar with French. I am not. I know how to pronounce that because that's what Google Translate told me. That's how it's said. Roche moutonné. Okay, this is what happens when a hill has the unfortunate destiny of getting in the way of a glacier. So here we have some sort of formation, a hill of some kind used to exist there. Glacier on its way downhill runs into that sucker. It doesn't say, oh, pardon me, and go around it. No, it shoves its way over the top, grinds its way over that, and kind of shapes it into this wedge shape. And you can tell which direction the glacier came from because of the direction the wedge is facing. The glacier shoved its way over, removing material, crushing it down, and then once it reached kind of this peak over here, kind of fell off the other side, and the ice just kind of kept pushing its way further down. So this is a roche-montagne, a hill or some other landform that just had the unfortunate fate of ending up in the way of a glacier.
It's getting the word rock, like transport though, at least.
No, I guess. Yeah. Oh, camera. Come on, for real now. There we go. Okay. Now, what about all that rock and debris that's getting deposited by our glaciers along this path? A lot of people call that glacial drift. I do not particularly like that name. That stuff didn't just drift there. It didn't just end up there. That name kind of sends the wrong impression, I think. I prefer the name till. Okay, till is a word that some people use. It's a lot better. As a matter of fact, you have already been exposed to the results of this. Do you remember in lab 3, I guess spoilers if any of you haven't done lab 3, there is a rock, a sedimentary rock that you saw called tillite. Tillite is what happens when glacial till gets compressed through the sedimentary process and becomes a rock. Yeah. Usually characterized by being sharp, angular, but sand-sized usually pieces. The pieces are too small to call conglomerate, but they aren't as rounded as your typical sands are. And there's usually not a whole lot of chemical cement, okay? It kind of just looks like I took a rock and I broke that rock or a bunch of rocks into a bunch of little sand-sized pieces, and then I kind of swept them all together, and I just kind of squeezed them until they became a rock, right? It's kind of what it would look like. So, till is the product of all that grinding and pulverizing of the ice on the rock on its way through that valley, okay? And when that material ultimately falls out of the ice, when the ice melts and that material remains, it's usually deposited in whatever body of water is at the bottom of our glacier. So much water comes off of a glacier, there's usually lakes or a series of streams that exist at the bottom of the glacier, okay? It tends to form into layers. We call this stratified drift or stratified till, right? Varves are another word that are used to describe these. And these are fantastic because we can use these to understand the length of the melt cycle and the, think of that as the summer cycle and the non-melting cycle or the winter cycle. Warm and cool periods. If I have a thicker varve, that usually means there was more melting going on because more sediment was deposited as it fell out of the glacier. If I have a thinner layer or no layer for that time period, I know that it was a cooler time period and there was little to no melting of that glacier. And so this is another example of how we can use these layers of rock to interpret things about Earth's past environment. Okay. All right, we're making good time. I'm going to bring this back out again. A glacial moraine is a deposit of sediment or rock on top of the glacier itself. Okay, so there are several different types. A lateral moraine, let's look at this picture here for a minute. A lateral moraine is the buildup of sediment and rock that you can see right here along the sides of our glacier. What's happening here? As the ice is scraping past the side of our glacier, it's pulverizing that rock, and that rock falls onto the glacier and goes along for the ride. It gets carried downhill. Think of glaciers as kind of like one big sediment conveyor belt on their way downhill, okay? Moraines, it's probably one of the easiest way to explain it. They're on a big conveyor belt heading downhill, okay? And lateral moraines, those happen along the sides of the glaciers, okay? So lateral moraine would be here. A lateral moraine would be there, and here, and here, and here, and here, and here, a lateral moraine right there. Okay, but what happens when multiple glaciers meet up? this lateral moraine and that lateral moraine combine forces, so to speak, and become a medial moraine. So take a look right here. It may not be that easy to see on the camera or on my wall, but that's why I provide my PowerPoints to you. You can see these in high def whenever you want, okay? You can see this lateral moraine right here and that lateral moraine right there. As these two glaciers met up, those two lateral moraines combined, and now you have one big medial moraine right there, this one. And then this lateral moraine and this lateral moraine meet up right here in the foreground of this picture. And now we have this medial moraine. Make sense? Lateral and medial moraines. Now, the third type of moraine is called a terminal moraine. That happens at the terminus or the end of your glacier, wherever that is, the front. Wherever it is currently melting, that's where your terminal moraine is being built up. So this is the front of a glacier. This is the front end, the leading edge of our glacier. Look at this big pile of sediment in front of it. As our glacier is slowly retreating backwards, it's leaving behind a bigger and bigger pile of sediment as that ice is melting. You can even see that right here. You can kind of see it on this model. That terminal moraine, that series of hills at the bottom of our glacier, that's the terminal moraine. But then when I take away the ice, it'll be that much more obvious. All that buildup of sediment right there, that's our terminal moraine. Okay, bring it over here so you can see it better. Terminal moraine. Okay, 3 types: lateral, medial, terminal. All acting as conveyor belts, taking all that sediment back downhill. All right, let's talk for a minute about what happens during these extended periods of cold. Ice ages, you may call them, the longer ones. Glacial cycles, you can call the smaller ones. We are actually just now coming out of a glacial cycle. Our ice age has been going on for a very long time. The last glacial cycle ended only 11,700 years ago. What do I mean by glacial cycle ended? Well, a glacial cycle is just when glaciers worldwide are advancing because worldwide temperatures decrease, right? Well, when that ends, that means that global temperatures have increased now and glaciers are in general retreating. That's the stage we're in. If we're not getting colder, we must be what? Getting warmer. So I just want to make sure that you understand this concept. Everyone uses the term global warming. And when I say global warming, what are your first thoughts? Earth is getting hotter. The way that you said that, explain that to me. No, just like the attitude that you said it with. Panic, right? Earth is getting hotter. That's how everyone thinks of it. Global warming. Ah! We're all going to die. If you've paid attention to Al Gore at any point in the last couple of decades, right? The icebergs are melting. We're all going to die. Okay? That's how everyone thinks of global warming. Yet, global warming started how long ago? 11,700 years ago. Long before we even had any sort of cohesive civilization. I don't want to downplay the situation, and I don't want anyone to say that I'm saying humanity hasn't played a role. I simply want you to understand that the warming of the earth is not unique to our time. It is not unique to the fact that we exist. Earth warms and cools. Granted, this one is much more aggravated because of our contributions. I'm simply saying we didn't start it. We made it a heck of a lot worse, but we didn't start it. All right? So I just want to make sure, I just want to set that expectation right there, that ground level for this discussion. There are lots of things that come as a consequence to both global warming and ice ages. glacial cycles. Usually extinctions accompany both. Things that can't adapt fast enough to the cooling temperatures, and then on the other side, things that can't adapt fast enough to the warming temperatures. Okay? Stuff dies out for both. I'll talk more in the next slide about some of the current theories for why we believe ice ages and glacial cycles occur. For now, just understand that they are cycles that existed long before we did. The things that we have done, namely application of fossil fuels in our industry, have released a lot of greenhouse gases. You've probably heard that term greenhouse gases before, right? I'll talk more about those when we discuss causes, but I'm kind of getting ahead of myself. I want to spend a little bit of time on this figure right here. I showed you a map earlier of what North America would look like, or the United States, I should say, would look like if all the ice in Antarctica melted. Well, now this is kind of the opposite image. This is what Earth looked like during that last glacial maximum, which ended 11,700 years ago, right? This particular image is 18,000 years ago. I said it ended 11,700 years ago. It began a lot further before that. But 18,000 years ago, this is what we're looking at. The East Coast is huge. Florida is twice, probably more than twice as big as it is right now. This is all dry land right there. So is all this. Baja California is huge. Matter of fact, Jamaica, Cuba, Bahamas, Florida, all connected. Okay? Land bridges between all of them. You can actually, right now, go out in a boat off the coast of Florida, go way out here, drill down into the ocean bottom, and pull up rock that was deposited while this was exposed to atmosphere. You can find fossils of ice age animals out there off the coast of Florida. And why? Because it was exposed for thousands of years. There were grasslands out there. Okay? This is how much continent is currently underwater because of melting rates. Okay? Also, look at how far south the ice came. Remember that mile-thick glacier I told you about? Look at all that ice. Why are the Great Lakes there at all? Because of that ice. This is an example of what's called isostatic uplift. Okay? Basically what happens is, think of a memory foam pillow. Y'all ever used a memory foam pillow, or at least seen it? If I had a memory foam pillow here and I put a bowling ball on it, what's that memory foam going to do? Sink down. Exactly. Then if I take that bowling ball back up, I may take it up quickly. How quickly is the memory foam going to expand back upward? Pretty slow. That's an example of isostatic uplift. If I put a mile of ice on top of my continent, that's a lot of weight. Mile of ice over all this area, and so it causes my continent to kind of bow down, to kind of get shoved further down into the mantle a little bit. That takes thousands of years. But if I melt it, geologically speaking, even if it took 1,000 years to melt, that's the blink of an eye, geologically speaking. It's not, that rock is not going to rebound upward nearly as fast. And so it's slowly going to push back upwards to regain its original position before the ice, that weight was put on it, right? Isostatic uplift. That's why the Great Lakes exist. That is a bunch of water that is currently sitting in depressions left behind in the continental crust by all that ice. Matter of fact, it's still rebounding. Eventually, it's going to reach where it was, or where it's content to stay. I know I'm anthropomorphizing it a little bit there, but bear with me, okay? Eventually, it's going to stop, but it is actually still rebounding upward. Right now, the Great Lakes are expanding. They are moving further out. Why? Because they are becoming less deep as the crust rebounds upward. As depth is lost, that water has to go somewhere, so it spreads out. And that's why cities like Chicago and all the other cities around the Great Lakes are experiencing more and more flooding problems. as the Great Lakes are slowly spreading out as a result of the decreasing depth. Okay. All right, so what is it that causes these glaciation cycles? Well, we believe they are tied to what we call Milankovitch cycles. Okay, this is the leading cause for glacial cycles today. What is Milankovitch cycles? Earth moves in 3 ways. You following along?
Yeah, because I have it in my social science.
Oh, nice.
You not every single week we do something different. It's every single day that we're taking a test is what you're teaching.
So I'm helping you study for 2 classes.
You are.
How about that? Okay, well, Jocelyn knows how to play the game. Okay. Earth moves in 3 ways. Eccentricity, that is our orbit around the sun. If my fist is the sun, we're moving around the sun, right? Doing this. However, sorry if that was very loud for anyone listening on the microphone right now. However, Earth does not have a circular orbit. It goes back and forth between kind of circular and elliptical. Kind of circular and elliptical. It goes back and forth. Every 100,000 years, give or take, approximately 100,000 years, we are either in an elliptical orbit where we are further from the sun and therefore receiving less radiation, or in a more circular orbit where we spend more time closer to the sun and receive more heat. It's obviously going to play a role in global temperatures, right? Okay. The next way, obliquity. That is the axis of the Earth versus the plane of our orbit. Notice how Earth in this globe is tilted. You ever looked at a globe and been like, well, why didn't they just do that? Well, that's because that's not what our Earth in space is doing. Okay? We are tilted like this. As we spin around our sun, the plane of our orbit around the sun, Earth is tilted at about, it wobbles back and forth, but like 22 to 23.5 degrees tilt. Okay, we'll talk more about that wobble here in a second. But we're tilted like so, and we spin. And then we have precession, which is that wobble around our axis. We are also doing this. As we do this, sorry if anyone's about to get dizzy. Earth is doing this in space. It's not very simple, is it? It's very hard to imagine that Earth can be doing this at all times, going around our orbit of the sun. It's kind of crazy. But those 3 things, eccentricity, obliquity, and precession, each of which is on a cycle. When these cycles add up at certain points, when we are furthest from Earth's or from the sun on our elliptical phase of our orbit, and also our precession and obliquity have added up so that more ocean or ice at a pole is pointing at the sun. Guess what? Ice, white, reflects energy. Ocean, what did we just learn about water? Absorbs heat efficiently, but slowly. And so it's kind of a perfect storm situation where every now and then we will end up at just the right time so that Earth absorbs less solar energy. If Earth absorbs less solar energy, what happens to global temperatures? They drop. And therefore, what happens to the snow line? It drops. And therefore, what happens? We get more snow deposited that remains year-round. We get more glaciers. More glaciers, more reflecting ice. So as we come out of that perfect storm situation, Earth has more ice on it, reflecting more energy. We absorb less, temperatures drop, snow line drops even more. It's called a positive feedback loop. And that's what launches an ice age or a glacial cycle, depending on the severity. Okay? Positive feedback loop. Now, what role have we played in this? We can't help this. The Milankovitch cycle's out of our control. That's just astrophysics, okay? That's out of our control. It's just the way it is. What we have done, though, is by our contributions of greenhouse gases. Do you know what greenhouse gases are? Greenhouse gases are large, more complex molecules of gas that absorb energy, solar energy, better, I guess I could say. They absorb more solar energy. There are larger particles in the atmosphere that inhibit the passage of solar radiation. Things like carbon dioxide and methane are a few examples of greenhouse gases, both of which we produce in vast quantities with our use of fossil fuels. So as more of these greenhouse gases enter the atmosphere, it's causing an effect. A certain amount of greenhouse gases in the atmosphere is good. We need them. Without greenhouse gases, solar energy would strike our surface and then bounce back off into space and leave. And we absorb very little of it. Without at least some greenhouse gases in the atmosphere, Earth would be quite cold. Matter of fact, as you'll learn in 1404, most of Earth's worst ice ages, including that snowball Earth effect that I talked about earlier, are because life absorbed too many greenhouse gases out of the atmosphere and caused an ice age. Yeah, life has caused ice ages that led to extinctions. Ironic, isn't it? We'll talk more about that in our next, in 1404. But what we have done is we have added more than the natural balance of greenhouse gases to our atmosphere. And these larger particles in the atmosphere have an effect. When a particle of light, let's say an alpha radiation particle, hits Earth, bounces off of Earth, having left a little bit of energy there, it's like, all right, I've done my piece. Now it's time to head back out to space, see ya, Earth. Instead of just being able to pass back out into space, it strikes a greenhouse gas particle, let's say a CO2 particle in the atmosphere, large enough that it reflects back to Earth. And so instead of zinging back off into space, it goes until it has left all its energy here, okay? And it stays inside our atmosphere. And as more solar radiation does that, Earth heats up. Earth heats up, snow line goes up, we reflect less, we absorb more heat. Global warming. We, by producing so many greenhouse gases, have aggravated that effect. This effect that occurs naturally on a cycle, thanks to Milankovitch cycles, we have kind of jump-started it, so to speak. We're already at a temperature increase that we should have reached somewhere around 800 to 900 years from now. And we are looking at the... Huh? Yes, normally Earth would be colder than it is right now. Exactly. We have increased the clock, is what I'm saying, with our contributions. And it's only getting worse. As a matter of fact, if the politicians' fake math could all work out and we could somehow end our addition of greenhouse gases to the atmosphere. Remember I told you politicians hate math? Politicians make promises and then a scientist tells them why it's not going to work and then no one listens to the scientist. If we could just cut off everything, all fossil fuels today, right now, we can't stop it. It's a runaway effect. It's already happened. People don't want to accept that. It won't take millions of years to reset. It would take about the same amount of time. Remember, we've simply sped the clock up. Okay? So where before maybe it would have taken 20,000 years to reach as bad as it's going to get, and we're going to get there in a couple hundred, it will take about 20,000 years to recover. Unless by some miracle we find some way to increase that. But I want to end on a philosophical question before we end for today. If we had the ability to change the climate right now, if I could snap my fingers and change the climate any way I wanted, for good or for evil, if we could develop technology that could change it, should we? I want to pose that question for you to think about for a second. We've already messed with it once. We made a situation that we couldn't comprehend at the time, but now we can't turn away from and we can't escape. Is it moral to, even if we think we're doing the right thing, do it again. I want you to think about that. And that's where we'll end it for today, unless you have any questions. No? Glaciers. Huzzah. All right. Well, I'm going to end the recording here. If any of my online students have any questions or concerns, you know you can always email me and I'll get back to you as soon as I can. Let me know if you need any tutoring. I'm happy to help in any time that I can make happen.